Professor Urbasi Sinha. She heads the quantum information and this is not working. That's okay. And computing laboratory. She's a Simons Emmy Noether Fellow at the Perimeter Institute in Canada and an associate faculty member at IQC, University of Waterloo, Canada, and CQIQC, University of Toronto, Canada. She completed her PhD and MSc in physics at Cambridge University, UK. She was a Gates Cambridge Scholar during her PhD and a Nehru Chevening Scholar during her Masters. She has a very long CV, so I'll go to the end. And she also got several awards. And today she's going to tell us about the Nobel Prize in Physics 2022.
So with that, of course, it's a tough act following up Rupamanjiriji in any forum. But I'm glad that, the topic is very different. So then this is the flavor of this conference, right? That we are going to sort of have some talks which are more optics related, and then some which sensitize us on who we are and what we want to be, right? And hopefully we also want to be people in optics and photonics. So sort of brings everything together. It is, of course, very nice and that, I actually get to talk about this in this forum, given that, there was no reason for us to know that the Nobel Prize in Physics 2022 would go to optics and photonics. So we organized the conference, and then somehow, somewhere in Stockholm, they heard us, and they decided to give this prize finally after, as Rupamanjiriji says, probably few decades of delay. And so this is where we are. And so the Nobel Prize in Physics 2022 was awarded to Alana Spey, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. So, this prize is, of course, very important. I mean, every Nobel Prize is important. But this time, I would say, from my personal point of view, it's important for two reasons. One of them is, of course, a personal reason in the sense that, my lab members, me, and many people in the audience are actually working with single photons, entangled photons, quantum information. So naturally, you feel a sense of, reflected glory, right? Like, this is where the prize has been given this year, so it's obviously very amazing. But the second thing which is important here is that, this is not just for the fundamental work that these gentlemen, along with many colleagues, have done. It's also for pioneering a field which is very technology-oriented. So the prize has been given for the science and the technology. And that is important, and I want to bring that through in the next, half an hour, 35 minutes that I'll be speaking, hopefully. Yeah. So that is why this is good, because, it's actually telling you about where we are and what we may be doing for decades, if not centuries. This prize lays the foundation for that. So before I move on to, so this is a shorter talk than what I would have, liked it to be, but today it's okay, given that, I have this interesting throat. I will tell you a little bit over the next 5 minutes about some of the basic concepts that, you just need to know a little bit before, so that you can appreciate the, the greatness of these experiments. But these are all topics by themselves, so I'll keep it very short and a little bit pedagogical, so that, everybody gets a flavor. But then some things you have to accept and go and read up a little bit, because otherwise we will never reach the end. So first topic, of course, is entanglement. Okay? And I know that Joey is giving a talk this afternoon on entanglement, so she can go all technical on that part. I will keep it at a level where, we leave flavor for it. This is our favorite cartoon in quantum world. We love cats, right? Whether it's Schrodinger cat, whether it's Cheshire cat, we have lots of cat analogies in the quantum world. So this is, Schrodinger's cat. And I know that the audience is mostly, students. So you would see things like Big Bang Theory and all these things where they made it very popular, this Schrodinger cat picture. So this is a cat which is, in fact, sitting inside an opaque box, okay? For illustration, you can see the cat, but actually you can't. So there's a cat inside a box, and the cat is sitting with a vial of poison, okay? Please remember, this is a thought experiment. So if there are, people who believe in animal rights, we all do, this has nothing to do with a real cat and a vial of poison. It's a thought experiment. So there is a vial of poison, there is a cat. So there are two possibilities. The cat has this poison or does not have the poison. But from outside the box, you don't really know what is going on. Don't worry about the meow and all that. So this is a thought experiment where the cat either has the poison or not, which means the cat is either dead or alive. But from outside, it is, of course, in some sort of a superposition of the two, because you don't know what is happening with the cat. You need a marker. So then comes this third element, which is a radioactive particle. So how the experiment goes, if the cat does not have the poison, the radioactive particle remains within the box. If the cat has the poison, the radioactive particle is emitted from the box. So it's like a marker. If I don't know whether you know about how elections are done in Italy for the Pope, for instance. There is this gray smoke, so Pope is elected, that kind of thing. So it's something like that. So the radioactive particle comes out or not, depending on the cat having the poison or not. Which means that this is the state we are looking at. A cat which is inside the box and hasn't had the poison is obviously a happy live cat. The radioactive particle is inside. If the cat has had the poison and kind of died, the radioactive particle comes out. So by looking at the state of the radioactive particle, you're able to know what is happening with the cat, which is an example of entanglement. So by looking at the state of the second particle, I know what is happening with the first. And that is where, this correlation matters, that the state of the particle and the state of the cat are correlated with each other. This is basically, without getting into all the math, some explanation of what is entanglement, this is how you can form entangled states. And this is an example I always like to take, that, there are people here, I'm sure you love music, as most of us do. So if you are in an orchestra, you can hear different pieces of music together, right? But if you hear them individually, of course, they would be beautiful. But when you hear it together, you hear this symphony that you wanted to hear. So together, the whole is more than the sum of parts. So you can't write it as a product of guitar times violin times cello. Essentially, you can't write it as a product of different separable states. An entangled state is something which is a correlated state which cannot be written as a product of its constituents. And so this is how we write it mathematically. You need not worry much about the form, but these are what are called the Bell states, which are the very famous states, because of course our talk is about Bell inequality and its violation. And this is a picture from the lab, of entangled photons. So here you have these intersection points. So otherwise you have the left photon and the right photon. But at the intersection point, it could be either left or right, because you don't know. If one is left, the other is right. If one is right, the other is left, but you don't know. And this indistinguishability is what is called an entangled state. So here we have the entangled photons. Okay. So second concept is locality. Okay. So now this is something I think, because we have many students, you would have studied special relativity. I'm thinking many of you have come from a physics background. This is Einstein. So this is what is called a space-time diagram. Okay. And so the idea being that, events which are within this, so this is called the light cone. Maybe most of you remember this concept. So inside, if the events are inside the light cone, they are called time-like separated, which means that you can have information go from one to the other at speed less than the speed of light. On the surface, it's the speed of light, and outside, it's space-like. So something inside and outside will be space-like separated, which means if something signaling has to happen, it will happen at speed greater than the speed of light, which of course we know is not possible. So that is superluminal signaling. So this is what is called special relativistic locality. So within the light cone is what is local, but Bell's locality assumption is stronger, and when we come to the experiments, we will see what that means. Okay. And now I go on to asking you some fundamental questions. The third concept is realism. Not a very easy topic, but then I'm trying to make it as holistic as possible. Many of you maybe don't work on quantum mechanics in your, maybe you're working in other areas of optics. But all of us, I'm sure, have studied quantum mechanics and have had this question. We talk about superposition, entanglement, and all these things. They don't seem very intuitive to us. Suppose, tunneling is a phenomenon. We've all read about it. You can solve the equation and so on. So if I went and, just ran into the wall, I don't think I will tunnel through. I will end up being also physically injured. Other than the throat, I'll have some more marks, right? So it doesn't happen in our daily lives, things like tunneling and so on. So, but then what does it mean then in terms of physical reality, these non-classical features? How to reconcile our everyday experience of what we call the macroscopic world with this behavior which is specifically quantum mechanical? And how far does quantum mechanics apply to the macro limit? Okay. This brings us to this concept called realism. And I will take an example to explain this to you. And I have done this before, some of you know this. So this time Rupa Manjari is here, so I will use her as an example. So she's, she of course knows this topic very well, but she's very kind, she's listening to me. And if I look at the screen, I think her kindness will persist and she will still listen to me. So her act of listening to me is not dependent on whether I'm looking at her or not. She's an attentive audience member. She won't look at her phone, maybe. So don't look at your phone. Okay, so then this is what I expect. So this is her state, her property of looking at me is independent of my measurement, which is actually whether I'm looking at her or not. So classical objects have predefined properties which are, irrespective of the act of measurement. So the tree outside will remain whether or not we are looking at it or whether we are going and sitting next to it and so on. So this is what is called realism. In quantum mechanics, that's not true. In quantum mechanics, you don't have any predefined property associated with a state. So you can have many possibilities. When you measure, you reveal the property that the measurement wants you to reveal. So this is what brings us to this very famous quote attributed to Einstein, that he likes to think that the moon is there even when he's not looking at it, which we would all like, in some sense. So this is realism, but that's not what happens in quantum mechanics. And that is what, so now, these three things that we have talked about, of course, entanglement, locality, realism. These are the concepts we just went through very, very quickly. So now if you use locality and realism as your assumptions, okay, then one can derive what are called Bell inequalities. Now, John Bell did precisely that, and so this is John Bell, by the way. And so in Bell inequalities, what happens is you have a source of entangled particles, let's say photons, and one of them, is sent to one of the measuring stations. The other one is sent to a second station, and what we do is we do measurements which are correlation measurements between these two. So we call them coincidence measurements. And so having said that, we can then define many such correlations of possibilities, the outcome being minus or plus. We can have 4. And this is where, I will not go into the derivation because we have a short time scale. So here, I would just ask you to, for instance, go to, if you want, I gave this talk a couple of weeks ago. It's on the RRI YouTube channel under the Vigyan Kathigelu series. I actually went through the derivation of Bell inequality there. So if you are interested, you can listen to that part from there. But for now, I will assume that we are all okay with Bell inequalities. Okay, and so I will, excuse me, skip the derivation. So what happens is that we can define. This is the CHSH form. It's called. We can define these joint probability measurements and we can form an inequality. So if it's less than equal to 2, it's classical. But if you now again go through the math using quantum mechanics, you will be able to see that it will become 2 root 2. So this is the famous 2 root 2, which is the Cyril-Son's bound. So between 2 and 2 root 2, things are not classically real. And 2 and less than 2 is what classical mechanics would give you. So all these experiments I'm going to talk about would measure different forms of these inequalities and see whether we are violating realism or satisfying realism. So this is the general idea. Okay. So this is what I wanted to really discuss in somewhat detail, because that is the prize. It's for the experiments. Of course, John Bell passed away. Otherwise, I'm sure he would have been a recipient of the prize as well. So the experiments that led to the Nobel Prize. Right? So the first experiment was by John Clauser and Stuart Friedman. This has a very nice story. John Clauser was an astrophysicist. So he did his PhD in astrophysics and he went to the University of California and he sort of joined a group which did radio astronomy. But he did that knowingly. He had developed a strong, liking for foundations of quantum mechanics during his PhD. And he knew there was a setup there, which was set up by, Kocher and Cummins, which was producing pairs of photons. So he wanted to use that setup and see if he could do an experiment to violate Bell inequality. But he was not a quantum optics person, so he got a job as an astrophysicist, convinced his supervisor, that I really need to do this experiment. So the supervisor then talked to Stuart Friedman's supervisor and said that, let's strike a deal that John Clauser will do this experiment for half his time, and Stuart Friedman would also participate with him. And so that is how the first experiment was something that someone did because of real passion. And that is probably a telling thing, because that is how things, really revolutionary things happen. That when you have this conviction that I really want to do this, so he brought himself an opportunity and came up with this first experiment. First experiments are always special because they are the first, but they are always not the best ones, because they will always have assumptions. And there are rest of the experiments which will become better and better versions, right? So there were many assumptions. Won't go through the details here. It was using a calcium atom cascade. These are the two photons which were correlated, so he used those. This was the kind of setup he used. Important is that he had these polarizer measurements. So by using different polarizer projections, he was able to do the joint probability measurements, okay? So the Ingenuity is, of course, the polarizer itself. So earlier, the polarizers were not efficient enough. So he used what is called a pile of plates polarizer, made it more efficient. That is why this experiment worked. So this was the main, experimental ingenuity. This was the inequality. They did many things to minimize errors and so on and so forth. So this is the, the experiment versus theory graph. And of course, importantly, this is the value he observed. And as you can see, and for the scientists here in the audience, you can see that, the value is 0.05, error is 0.008, which means the value is much more than the error, which means that it is a strong non-zero. That is what we're trying to see here, whether it's zero or non-zero. And non-zero means that, no evidence of deviation from predictions of quantum mechanics, and strong evidence against local hidden variable theory. So this was the first experiment, provided a very strong evidence, but had some, assumptions, naturally. Otherwise, why would we have all these other experiments? And so this is very important to just take a pause here to realize that, for people who are not from the field, you have to understand that this is a series of experiments done over decades by different groups towards one end goal, to have an experiment which does not have any loophole or does not have any other way of explaining what we are doing. And so this is like a community coming together to keep doing one experiment after the other, which sort of recognizes the previous one but improves upon it. And so we need concerted funding for such things. And this is something, we are missing a little bit these days. Everything has to happen in a day or two. That does not happen, right? So this is a series. And of course, one more thing I want to say here, that the 1980s was not only important for Alan Aspect and his experiments, but we have Rupamanjari Ghosh here, who actually, Ranjini already mentioned, pioneered, along with her colleagues Hong, Oh, and Mandel, this two-photon bunching experiments, which is, quintessential quantum optics experiments. Quantum optics was really thriving in the 80s, and we have someone here who was equally responsible for that. And so this is Alan Aspect and Gerard and Philip Grangier. I didn't find a picture of Gerard Roger, excuse me, on the internet. So what did these guys do? Okay, again, a calcium cascade. We have a similar coincidence measurement. So what was their ingenuity? Same inequality, but then the violation was more than 13 standard deviation, much stronger. So that's what happens. You get better and better and more stronger violations. But the important thing also they did is that they, moved the polarizer away from the source. So by 13 meters, which actually had some significance. It's to do with what is the speed of light and how much information can go from one to the other. So they moved the polarizers away. And so this is important because, no effect was found of the distance between measurements on the correlations. So this was the first time someone tried to actually change the distance and see what happens, other than, of course, the very strong violation. This was Alan Aspect's first Bell violation experiment. The second one, again with same collaborators. So this now brings us true to the spirit of the original EPR Gedanken experiment, what we call the EPR Bohm paradox. You've heard about this. So what was proposed, and we saw earlier in a slide, that you have a source, you have a pair of particles, they go, one goes here, one goes here, and you have these measurements. This wasn't the case in the first few experiments. So this actually requires measuring these 4 terms simultaneously. So you have to be able to measure all 4 terms in the same run of the experiment. That wasn't possible by the Clauser experiment or the first ASPE one. Okay? And so why? Because they were using polarizers which were more like analyzers. So either the photon goes through or it does not. So it was only one or the other. There was no way in which they were changing the projection in those first experiments, including ASPE's own. So only they could measure one of these terms, plus plus AB. But these guys could not be measured in the same run. They did different runs, combined them, and experimentalists know that means errors. If you do many runs and combine the results, that is not going to be as good as doing it in the same run. And so this is what happened. And so what does this mean? So when you have, in the different runs, the detector becomes an issue because they are using what is called the photomultiplier tube, has a low efficiency. Because of this low efficiency, whether the photon has gone through or not is one question. Whether the photon has been detected or not is the other question. We are interested in the first one, but the second one comes as a natural, buy one, get one free. And so this is something the previous experiments could not solve. And so that is where these guys, this is their ingenuity, that it was very close to the EPR-Gedanken experiment, and they used polarizing beam splitters for the first time in a Bell inequality experiment so that they could do all 4 joint measurements at the same time. And, excuse me, very similar to the Stern-Gerlach experiments, which I'm sure you've all read, for spin-half particles. Okay, so 4-fold coincidence technique, all 4 in the same run. This is their, term that they are measuring, and they have done many things. But then, importantly, you can see experiment was this. Quantum mechanics predicted this. So naturally, a great, match with quantum mechanics. Strong violation of local realism, and also using an experiment where we did not need to combine results from many runs and do something. So this was very important. And strongest violation achieved till date, an excellent agreement with quantum mechanics. So obviously there are caveats. We are in 1980s still. So how would we come to the other experiments? So there is this assumption which is called the fair sampling loophole. Now this is a very important assumption which has to be closed. What does that mean? It means that you have a detector. No detector is 100% efficient. So if you have something, impinging on a detector, some of them will be detected, some of them won't be, because it's a quantum efficiency is 60%, 70%, something like that. So there are going to be few photons which will not be detected. So 30 are not detected, let's say 70 are. So the 70 which are detected, they are violating Bell inequality. Fine. But what about those 30? Maybe they don't. We can't say because we don't detect. So this is this assumption that my sample is fair. But what gives us the right to make this assumption? Well, we are limited by what we have. We don't have better detectors in this stage. But then this remains a loophole. So there is an alternative explanation that comes through. So this is 2 loopholes remain. This is detection efficiency or fair sampling loophole. This is the one we just discussed. And the other is the freedom of choice loophole. These words sometimes make you think of philosophy, but these are real experiments very far from philosophy. So the idea is that, you have these polarizers, they are fixed. Your photons are going, they're going this way, that way, you're doing measurements. But then how do you know that the static character does not bring in some bias? Because so once the photons leave, there is nothing that we can do to change the polarizer setting randomly. So there is this, we are making a freedom of choice here, which is a problem. So we need to randomize that part. So these 2 were not closed by the first 2 Alan Aspect and his collaborator experiments. Okay. Then comes this one, which is of course a very seminal experiment with John Dalibard and Gerard Roger, where this again it's a little bit of a hard concept, but I'm going to try and explain it to you so that you get something out of it. So this brings us to what is called Bell's strong locality condition. So all experiments have been performed, excuse me, with static setups in which polarizers are held fixed, as we just discussed, for the whole duration of time. One may question then Bell's locality assumption. The states that the results of the measurement of polarizer 2 does not depend on the orientation of polarizer 1. This is what Bell really wanted. But then how do you know that is happening? Because there is nothing changing. The polarizer is not changing once the photons are emitted. So, but then, there is no fundamental law which says this has to work. So Bell himself, points out the settings of the instruments are made sufficiently in advance to allow them to reach some mutual rapport. Okay, so you do some sub-experiments before the main one. You just discuss with each other. So Shwetashri and I are doing this experiment. We are discussing with each other that, when you get this, then I am getting this. When you are getting that, I am getting that. You make a little table, which you both know. Then there is no randomness anymore. So when you're doing the experiment, even if we are not talking to each other, we have some sort of a map that is allowed so far, because nothing is changing. It's static. So this is what really worried Bell. Okay? And because nothing would hold then. All these conditions would break down. So he insisted on the importance of experiments in which the settings are changed during the flight of the particles. Okay? And so this is what this experiment does. Okay? So I'll skip the details here. This is the important thing, that instead of actually having a static polarizer, they used what is called an acoustoptic modulator. And I think we all are familiar with what that is. Light can be switched. So you have an acoustoptical interaction. So there is light. It is interacting with an ultrasonic standing wave in water. And so this is making the beam either go straight through or deflect. So this is brought in as a switch. The concept of an optical switch is brought in to bring about a dynamic character to my polarizer settings. Okay, so this is what he did, he and his collaborators. And by following various, times so that speed of light is not violated. Okay, and so this was their beautiful result. And okay, so then are we done? No, we're not. Not we, or neither were they. We still have not done everything that there is to do. We have brought in a dynamic character. But now what? What next, really? The new feature is that settings of the polarizers are changed at a rate greater than C by L by using this optical switch. The ideal scheme is not completed because it's still quasi-periodic. This is a switch. There is no randomness associated with the switch. We need randomness now. So this is what we need, a more ideal experiment with random and complete switching for a conclusive argument. Okay? And the next work reports this ideal experiment. And this is by Anton Zeilinger, our third Nobel laureate in physics this year, and his group, Gregor Weiss, Thomas Genewein, Harold Weinfutter, and Christoph Simon. So this is that experiment where they have been able to achieve sufficient physical distance between the stations and ultrafast and random setting of the analyzers, and also completely independent data registration. So that also, they don't do just coincidence. They take the data independently and then post-process, so that there is no way in which you can influence each other. That is what we are trying to achieve here, right? And of course, Gregor Weiss and Thomas Genewein were here at RRI for our lab's inauguration. This is them. So somewhere, Rupamanjiri, I'm like little academic granddaughter of one of the Nobel laureates. At least I can be happy with that thought process. But Gregor and Thomas, were my postdoc mentors at IQC. So what is needed to do this? Obviously you can see the complexity is increasing as we are going to newer and newer experiments. And so this was what it was, that, this second loophole remained open because there was a switch which was quasi-periodic. So I will point to the main thing, that the individual measurements have to be so quick that it is impossible for any information about it to travel via any channel before the other guy finishes his measurement. So this quickness has to happen in a random way, and need for a physical random number generator, not pseudo-random number, because then it is predetermined. And so this is what they did, and independent and highly accurate data time basis on both sides by using an atomic clock even for the first time. And so this was their space-time diagram, and this is across the University of Innsbruck campus. The Alice and Bob were set up there. So yeah, so essentially they were separated 400 meters, as I mentioned, and also 1.3 microsecond is what we need so that there is no direct communication faster than speed of light, and it was much faster than that, their experiment. and they used physical random number generator and fast electro-optic modulators. In 5 minutes, I will ask you whether you remember this. That is how this is planned, so remember this. And independent data registration, atomic clock, type 2 SPDC, which is what we do. First time, spontaneous parametric down conversion comes into the picture, which makes it much, much brighter than the calcium experiments. And APDs, silicon APDs, not PMTs. So those who know what I mean, much faster, much more efficient, less dark count. This was the setup. Again, beautiful experiment, 30 standard deviations violation. Okay. So which major loophole remains to be closed? Fair sampling. Still we have detectors which are not 100% efficient. This is a very interesting, humorous comment from Bell, that it is hard for him to believe that quantum mechanics works so nicely for inefficient practical setups and is yet going to fail badly when sufficient refinements are made. So he said that, fine, I don't worry so much about it. You make it time varying and random, I'm okay. But still we need that final experiment, which is the next one, right? So this is the final experiment in this saga by Anton Zeilinger, and now so many people that I didn't put pictures because it's a bit odd. And so this is the first loophole-free violation of the Bell inequality. So no loophole remains. So we have gone and closed one after the other, not we, but the various Nobel laureates and their groups. And so this has closed both locality and detection loopholes simultaneously. So this is a loophole-free experiment. Ranjini, I have 15 minutes. 13. Because now I have to have this. Just give me one second. So we dwell on this. Very important slide. So why is loophole-free important? Why is loophole-free important? Anita, why do you think a loophole-free experiment is needed? Okay, so then I answer that question for you. This is the timeline. So this is when John Bell proposes, and 2017 we have the loophole-free. So decades we have taken. So why is loophole-free important? Well, of course, loophole-free means there is no alternative explanation to what you're saying. Everything has been closed. What you're saying is what is true. So that is, of course, fine, which means quantum mechanics is right, local realism is not. But then there must be more to it. And the more is what makes this interesting, that, now that I have no alternative explanation, I can use this for the purpose that we are using it now, which is high security. So the security in communications, you can't use something if there is an alternative explanation to it. That, okay, my security is there, but then there is one loophole. Maybe that won't work. So loopholes have to be closed so that you can use it for secure communication, random number generation, all these things which we are doing. So that is why loophole-free is important from scientific and technological point of view. And with that, I want to make a little this thing here that we did the first loophole-free experiment of the Leggett-Garg inequality. We talk about Bell so far. Leggett-Garg inequality is the time equivalent of the Bell inequality. And after several decades of the community also coming together to attempt this, our group at RRI actually managed to do the first loophole-free experiment for the Leggett-Garg inequality. So this is indeed a very proud moment for us because it also coincides with the year when loophole-free has achieved so much recognition in the general domain, right? Now, this is our violation of Bell. I will skip that just to show you that graph, which we have become so used to seeing. So anything above this is where you have the violation. Okay, so again, coming back to Anita, so this is what we have just discussed, the whole history behind, the loophole-free. But this is what is important. This is from the Royal Swedish Academy website, that, it's not just this. So these QKD protocols depend on Bell tests. So the issue here is not that whether nature conspires to violate Bell inequalities, but whether the evil eavesdropper does. So now we have the ability to beat an eavesdropper with a quantum computer. So the best possible resource that an eavesdropper can have, she can have or he can have, and we can still do an experiment which is secure. And that is why these are phenomenal results. Okay? The switch, if you remember, I told you to remember the switch. So these are all experiments in modern times which are using the switch for quantum key distribution. Okay? So now this is where we are going, and so the next 5 minutes I will tell you about what this has achieved for us as a community. Other than, of course, our liking for quantum mechanics being ratified, but that's not enough. what has it achieved for us in terms of technology, and why? And I was asked this question last time I gave this talk, why is the common man benefited? And so to answer that question, the common man is benefited because we all care about security. We don't really trust each other, or for that matter, maybe we trust each other, but then overall we don't. So we have to keep things secure. So security in communications is enabled because of this year's Nobel Prize. That is why it matters to us. And this is where we are going, where we connect the whole world by using the Global Quantum Communication Network. Okay? These are various ways. So Anton Zeilinger's contribution to this year's prize is not just the loophole-free experiment. He actually has done the first experiments in very important quantum communication ideas, which are called quantum teleportation and entanglement swapping. So this is the first quantum teleportation experiment with Zeilinger and his colleagues. Jianwei Pan is, of course, a very famous colleague of Zeilinger who has gone on to do the first satellite-based quantum communication in recent times from China. Okay, and so this is, of course, teleportation. I'll skip what is teleportation. It's a means of quantum communication by using entanglement as a resource. It's not key distribution. It's different from key distribution, but it's also information transfer protocol. Okay, and so these are the current results. So these are increasing in distance, as you can see, 16 kilometer, 143 kilometer. So very, very thriving and a lot to look forward to. That is what makes this so exciting. It's not just been there, done that, old hat. That's not this year's prize. It opens up things to do for all of us and beyond, right? So these are ground to satellite teleportation. As you can see, so many experiments. This is entanglement swapping, again, the first experiment. This is the third reason why he got the Nobel Prize, okay? And entanglement swapping, Ranjini, is something that I'm sure you will appreciate, given that you must have played the relay race. You appear like a sports person. Yeah, so then, you would run with this baton and give it to someone else. That lady or gentleman will run, give it to someone else. That way, this guy gets transferred over long distances. We do that with entanglement. We keep increasing the distance over which entanglement is transferred by swapping it between different photons. In this case, for us, it's human beings. So that is entanglement swapping, increases the distance of communication. So now, entanglement swapping, again, very popular topic, lots of research happening in modern times. If you include swapping along with memory, you would get a quantum repeater. That is one way of increasing the distance, because beyond a point you can't keep doing this, because somewhere you will be out of sync. So you need to store the information, so which is where the memory element comes in. Once you put a memory, you can have a repeater. And that is where you have the current research happening. Very nice work from various groups. Device-independent quantum key distribution. This year, 2 experiments have finally happened, and we have been looking forward to this. So what does this mean? It means that finally, even if my device is compromised, even if, my device is aging, which happens with every device, I can still do QKD, which is highly secure. And that is what is enabled by the Bell inequality violation experiments that the Nobel Prize winners have done. So this has enabled this, for instance. Random number generation, again, another story where, the security of many things is dependent on the availability of random numbers. So how random is that number? Is it predictable? How far can you go? Again, make it device independent. That happens from violation of Bell inequalities. Again, something that we are working on quite a lot in our lab. And then, of course, satellite-based secure quantum communications. Another, application which has been cited in the Nobel, Swedish Academy page. So this is what it means. So increase the distance, that's what we want to. So Anita and I, we want to talk through a satellite in a secure way and not using Google Meet for the future versions of this conference. So that is what we'll be able to do. Of course, we don't have any secrets, but if we did, it would be secure, right? Because that is the distance we are trying to achieve here. And we are doing that through our own project, We have this is the first project that we have in our country on satellite-based quantum communications. So the idea is we are going to have quantum key distribution between 2 Indian ground stations using an Indian satellite as a trusted node. And so we have achieved many ground-based milestones. Now we are working on the satellite phase. And we are, of course, very pleased because, this is the first such project and has given rise to so much excitement in various sectors. And this is one of our, results where we have this very nice protocol which has a very high key rate and QBER, which is globally competitive. But what is important is, if you remember, I told you to remember something. this physical random number generator that the Zeilinger experiment used is what we are using for the security being so high. So, nothing is dated in our Nobel Prize this year. It's all being used by people around us all the time. So this is what brings us to, what sums up the prize, that, the prize has been given for the science and the technology. And it's beautiful, although it took several decades. But then maybe it's, thankfully people are all alive also, except John Bell. But then it's good because then the prize also pays, homage to the various technologies, which otherwise would not have seen the light of day had it been given in 2000, let's say, when, and the loophole free also would not have seen the light of day. So it's, I think it's okay because, the people who deserve the credit got it and enabled this technology, which is so amazing to us and beyond. So thank you very much.
Thank you, Urbasi, for a very interesting talk. Questions?
It's very nice to know that the hackers have been put in place. Having said that, which of these experiments actually reached the Cyril-Simms bound?
Oh yeah, so the Zeilinger experiment, the loophole-free experiment, that one is pretty much 2√2. But then just to add to that, the idea of these experiments is to make it loophole-free. The Cyril-Simms bound record is with the Singapore group, where they actually reached 2√2 with a very small error bar. So there was an experiment, like I think 4 or 5 years ago, from Alex Ling's group, which was
Calcium.
Alexander Ling.
Calcium, or
No, not calcium. No, I mean you wouldn't want to use calcium for the for reaching these bounds or breaking efficiency barriers. It's all SPDC. Yes. Good. So it's because people have
No,
followed.
but I have a question.
Oh, okay, great.
And because
Yes.
I work on, classical statistical mechanics, I think I can get by, asking dumb questions.
Those
So,
are the tough ones. Yeah.
okay, thank you. We'll see. So, so where you showed the entangled photons from your lab right at the beginning, the rings, yeah, I wanted to know why they look like rings.
Ah, yeah, that's a good question. So it's not dumb.
Okay, thank you.
Sorry.
That's good to hear.
We
Okay.
just know each other very well. So, what happens is these photons are emitted from the crystal. So I had a video which I didn't show because it's
Right.
not at top.
Okay.
So they sort of, they traverse a cone. So there's something called Selmayr equations that you need to solve, which actually gives you the trajectory of these photons. So for these
Okay.
particular SPDC sources, they traverse a cone. And of course,
What
we
is
can only
SPDC?
spontaneous
Single
parametric down
Oh,
conversion.
okay,
So it's a nonlinear
okay.
optics process.
Okay.
And that is what has led to these loophole-free experiments and beyond.
Okay.
So the calcium ones wouldn't do it. So now they're traveling in the form of a cone, but of course you can only measure a slice, right? You put a camera, so that will going to give you circle. And that is how, so it's a very highly intensive camera. It's a, it's CMOS. And so we have collected with a period of time, and then, you see the illumination of the photons. But please remember that at a given time, only one point on one circle and the other point on the other circle are getting populated. But this is an integrated image. So that,
Right.
yeah.
Right. Over what kind of time?
This was 60 seconds.
Okay.
Yeah.
Okay.
This is called spontaneous parametric down conversion. So it's a nonlinear optics process. So you have a nonlinear crystal, you have a strong laser beam, and 1 in 10 to the 8 or 10, they split into 2 photons. And there is a lot more math that I'm skipping here. But so essentially it's called the twin photon effect. So always it's pairs of photons, and they are produced at the same time. And so that's why you can measure one, you know the presence of the other. That's how you get a single photon.
Okay. Another question. We are running a little late, so I think we'll make it the last question.
Sure. Yeah.
I want to know about quantum steering. Which one is more better, like quantum steering or entanglement in non-local correlation?
Quantum steering is enabled by entanglement. So, it is another way in which you can use entanglement as a resource to achieve something. So I don't think the question overall I mean, so they are different parts. So entanglement is necessary for this to happen, whether it is remote state preparation, whether it's quantum steering, whether it is, teleportation. So it is enabled by that. So
Steering is a part of entanglement.
no, steering is enabled by entanglement, like so many other protocols are. So entanglement is the necessary resource in all this. And that's why even, the prize goes experiments on entanglement, Bell inequality violation, and pioneering quantum information science. So the first part is what you are covering, but maybe getting a little mixed up. We can discuss offline.